Today we are going to look at matrices and their row operations. Today is going to front load a lot of skills that we are going to need for 3.4, which is going to be solving matrices with Gaussian elimination, but we're just going to talk about the basics today. So a matrix is a rectangular array of numbers representing a system of equations. Typically, when you look at a matrix, it is going to have dimensions, and the dimensions are going to be the rows, and rows typically will go left, right, by, and that's usually us just saying the word by, and then we have columns. And our columns are the vertical up, down. So anytime you go in to use matrices for solving, you want to make sure that you know how many rows you have and how many columns you have, because that's generally going to tell you how many equations you have and variables and answers. So in this case, when I look at example 1, typically for all matrices across the board, they're always labeled with a capital letter. So this is going to be matrix A. And if I look at matrix A, I can count that it has 1, 2, 3 rows, and it has 1, 2, 3, 4 columns. So when I go in to write the dimensions, this is going to be a 3 by 4. So 3 rows, 4 columns. Now, something that we like to include just in case you see notation like this on one of your TSIs or ACT or PSAT is going to be the entry address. So if I see lowercase a in this case, and it has a little subscript next to it, this is just telling me to look at row 3 and to look at column 2. So again, you will always be reading the row number first and the column number second, just like when we write the dimensions. So I go to row 3, column 2, and it looks like the entry in the matrix at that location is going to be 2. So A32 is equal to 2. Now for the reverse of that question, what is the address of the entry 8? So I go in, I figure out where 8 is, and then I just look at what row is it in and what column is it in. And so in this case, the row is going to be row 1 and the column is going to be column 3. So my address for entry 8 is going to be A with a subscript 1, 3. Now, the real purpose of all of this is so that we can solve a system of equations a little bit easier than if we were doing substitution and elimination by hand. We're still doing it by hand, but we're kind of taking away the fluff of an equation. So the first thing we have to kind of practice is how do we convert back and forth from a system of equations and a matrix. So one thing I like to point out is every time you look at a system, the number of rows you have is going to come from the number of equations that you have. So I have 2 equations. I should end up with 2 rows. So dimension-wise, this is going to be a 2 by. And then every single variable that you have is going to have its own column. You have to make sure that everything is lined up. So I have a column for X, a column for Y, and a column for our answers. Now, sometimes you will see these matrices with a little line kind of splitting the variable side from the answer side where the equal sign is, but it's not something that has to be there. So in this case, we have a 2 by 3. So I like to come in and I like to kind of give myself some space to write out my entries. And again, I'm just going to show you one where the line is there with the equal sign, but again, it doesn't have to be. So what we do is we're going to look at this system, and the only thing that you're going to pull from the system is going to be the coefficients, so the numbers in front and the answers. So my first row of this matrix is going to be +5, +6, -10. And then I'm going to do the same thing with the second row, -3, positive 8, and 15. Now, the reason why it's so important that you go in and you make sure these things are in order is so that you don't get anything mixed up when we start to use these matrices for solving. So that's all we have to do. I have converted from my system of equations to my matrix. Now, the next one is going to be a little bit different because, for example, 2's first system, everything was already in order. Everything was organized for me. I just had to go in and put it into the matrix. When I look at my second one, I can see that things are currently not in the order they're supposed to be. Typically, everything we do is alpha order. So I'm going to take this system and I'm going to rewrite it. Anytime you have a variable missing, you're going to go ahead and fill it in with a 0. So since there's no y variable in the first row, I'm going to write 0y. And I'm going to go ahead and write 1z so that we know that if there's a single variable by itself, that is going to be a 1 in its place. Now for the second one, it's a little tricky. I typically like to move my x, y, and z to the left just to kind of keep things in the same order, so you're kind of doing the same thing every single time. So I have a 1x, and if I were to move that 2y to the other side of the equal sign, that's going to be minus 2y. And then if I were to move that minus z to the other side of the equal sign, that would be plus 1z is equal to 8. And then I jump down to my last equation. There is no x. There is 1y. And there's minus 2z is equal to 12. Now from here, I can see that I have 1, 2, 3 rows, and I have 1, 2, 3, 4 columns. So I'm going to go ahead and write out my matrix. Again, you can have that little line separating your variables from your answers, but it's not required. So I'm going to go in and pull from my first row all of the coefficients, and then I'll pull from my second row all the coefficients, and then finally from my third. So one of the big things when we get to actually using these for solving is that when these are in line, we're hopefully doing an elimination style. And so in order to be able to eliminate, you have to make sure the variables are all lined up, if you remember from our solving by elimination on 3.1. So all I have to do to convert is just take all these coefficients, make sure everything's in order, and we are done. Now, kind of dipping our toe into the water of why this is important. If I go to example 3, this is asking me to convert a matrix to a system of equations. So I'm kind of going to do the reverse of what I just did. So first things first, from the matrix, you don't really know what the variables are, but typically we go in and we still just use x, y, z, and these will be our answers. So you'll notice it has that line there. If the line wasn't there, we always assume the last column is the answer column. So I'm going to go in, I'm going to have 4x plus 2y minus 1z is equal to 8. Second equation is going to be 1y plus 2z is equal to 10. Third equation is going to be 1z is equal to 4. Now, on the next lesson in the Gaussian elimination day, we are going to focus on trying to solve these systems of equations. The big goal of that process is going to be trying to make it so that when I look at this matrix, there are 3 zeros in the bottom left-hand corner. The reason why we want to do that is so that it makes it so our system is already solved for one variable. If I go in and I look at z, I can tell from what I have currently that z is equal to 4. And sometimes it's not just 1z, it may be like 2z is equal to 8, but that is still something that you can easily solve. And so once I know what z is, I can kind of come in and take that value, so in this case it was 4, and plug it in. And usually the reason why the 3 zeros are really nice, you can plug it in directly into the equation above, and it's going to make it so that you can solve for y. So in this case, I could go in y plus 8 equals 10, minus 8, minus 8, y equals 2. So I have my z, I have my y, and I can take both of these and plug into the top equation. So 2, and we just found out that y was 2, minus 1z, which is 4, is equal to 8. And so I'm going to get 4x plus 4 minus 4 equals 8. The plus 4 and the minus 4 should cancel each other out. 4x equals 8. So if I divide by 4 on both sides, x is equal to 2. Now, if you remember what we did when we were solving 3-variable systems, you're going to want to take your 3 answers and you write them as an ordered triplet, and it's always going to be in alpha order. So in this case, it'll be x, then y, then z. So 2, 2, 4. Now, with what we will do in Gaussian elimination, we're going to take something called a row operation, and basically it's the steps that we normally do with elimination, and we're going to try to make it so that even if I get matrices that look like this, where there are not 3 zeros in the corner, I can take this matrix and turn it into one where there are 3 zeros in the corner, and I can go on to solve it for x, y, and z. So let's kind of talk about what those operations that you can do are. So there's 3 things that are allowed. You can do row switching, which basically just means you can change row 1 and row 2. If I write an equation and the first equation is 0, 0, 1, 5, the first row is 0, 0, 1, 5, I can just move that to the bottom and I'm almost done. Now, one thing that I usually recommend, the order that you go in when you do this, I will usually start, and it doesn't always have to be this way, but I'll usually start by trying to make this first 0, and then I'll move to this second 0, and then I'll move to this third 0. And that usually works 9 times out of 10, but sometimes we'll have to kind of take a different approach when I already maybe have some zeros in my matrix. Now, the next thing you can do is you can multiply a row or divide a row by a non-zero value. So I can take any row and multiply it by 2 or 1/2 or 5 or 10. However, I can't take 2 rows and multiply them by each other. Now, what I can do is I can add or subtract 2 rows from each other. So think about elimination again. We would take 2 equations and make sure they had opposite signs so that we can add them together and a variable would be eliminated. It's that same idea. So you can add or subtract 2 rows to create a new row. Now, the one thing you have to be careful of is I can't add a number to every single row, and I can't multiply rows by each other. So make sure you keep your operations kind of in your brain separated. So the first thing we're going to do is we're going to kind of go through some of the common row operations that you might see. One little thing that I do want to point out is if we ask you to write an augmented matrix, that is just the matrix where you've taken a system and you've written it as the numbers only in a matrix. So in this case, when I go to look at letter A and I want the augmented matrix for this first system, I can see that there is 1x, 1y, 1z, and 10 is the answer. 2x, 1y, 1z, 12 is the answer. And then in this last one, you have to be really careful. I have 0 x's and I have negative y. And so because we're not moving it from one side of the equation to the other, this is still going to stay negative 1. It's not going to turn positive because I didn't actually add it to both sides. We're going to keep it at -1. And then I have 1z, and the answer is 3. So I'm just going to go down the line really quick, and I'm going to write all of these augmented matrix so that we can kind of see how that's done. And then we're going to talk row operations. So for B, we have 2, -1, -3, 0, -1, 0, 1, -8, 1, -4, -1, 3. So again, all I'm doing is pulling those values, those coefficients, from each of my variables and writing it in line with each other. Now, these last two appear to be in order already, so I don't have to do much other than just pull those coefficients out. Now that I have my augmented matrices, I can go in and perform the row operation. So let's kind of talk notation. Whenever you decide what you're going to do for these row operations, you always have to write what it is. So the first thing I kind of want to point out is usually when it's equal to a single row, that is going to be the row that ends up changing. So row 2 is going to change for this particular row operation. Anytime I know what row is going to change, I go in and I just write the rows that are not. And trust me, one of the biggest downfalls of this process is going to be organization. You need to keep your work organized. So if I'm not changing row 1 or row 3, I'm rewriting them exactly as is. Now in this case, it's saying that row 2 is going to change to be row 2 plus row 1 added together. And that is an okay operation. We can add 2 rows together. We can't multiply 2 rows. So I'm going to go ahead and highlight my row 2 and my row 1 so that I know what numbers are going to be added together. So I'm just going to go in. 2 plus 1 is 3, 1 plus 1 is 2, 1 plus 1 is 2, and 10 plus 12 is 22. So we went ahead and we did our operation. Now, the one that a lot of people struggle with is going to be subtraction. So in this case, when I say it's equal to row 3, that means row 3 is going to change. Now, be really careful with subtraction because the order is going to matter. I am doing row 1 minus row 3. But since I know row 1 and row 2 aren't changing because that's not what I have it equal to, I'm going to go ahead and just rewrite those. So I like to highlight. So I know row 1 minus row 3. So row 1 minus row 3. Be really careful if you have double negatives. So 2 minus 1 is 1. -1 minus -4 turns into -1 plus 4, which is just going to be 3. And then -3 plus 1 is going to be -2. And then 0 minus 3 is -3. I can tell you this, the most commonly missed row operation that we see is the subtraction. Be really, really careful. Again, keep your work as organized as possible and don't rewrite things that you are not changing so that you don't mix them up. Okay. Now, realistically, because you're going to be the person that selects the row operations we do for Gaussian elimination, when you go in and you pick your row operations, you are going to most likely kind of do 2 things at once. It's almost like elimination when if I wanted to eliminate a 2, I'm using a -2, so I rewrote my whole equation times -2. That's kind of what this process is. So a lot of the time you're going to be multiplying and adding or multiplying and subtracting. So because the goal again will always be to get zeros in those corners. In this case, we're going to do 2 things. The first thing we're going to do is we're going to go in and we're going to multiply all values in row 1 by 2. Now, sometimes if you want, you can absolutely change that row if it's something different. But a lot of the times I just recommend somewhere near the row that is being changed, write out what those multiplied values will be. So 1 times 2 is 2, 1 times 2 is 2, -8, and 24. I know that you probably are capable of doing this in your head, but I can say I do think writing it down helps a lot. So now that I know what 2 times row 1 looks like, I'm going to take 2 times row 1 and I'm going to add it to the existing row 2. So I'm really just ignoring the original row 1 for the time being, and I'm focusing only on this doubled version. So now that I've done that, I can go in and kind of combine these two things together. So 2 minus 2 is 0. 2 plus 3 is 5. And I know I said 2 minus 2, but if you do 2 plus -2, that's like subtraction. -8 plus -1 is -9, and 24 plus -5 is 19. So we are just going in and practicing these row operations so that when we get to our Gaussian elimination day, you can kind of make these decisions yourself so that you make that end goal of the 3 zeros in the bottom left-hand corner so that we can do something like example 3 and solve easily for x, y, and z.